And now we start with the first talk by Matteo Bachetti. Matteo is a researcher at Observatory of Cagliari, and he's going to give a talk on CICLOPS, the citizen computing pulsar searches.
Thanks a lot, Francesco, and thanks to the organizers for accepting my talk. So what I'm going to tell you today is something about CICLOPS, which is a game designed for pulsar searches. So for those of you who don't know pulsars, pulsars are extremely dense objects. They're stars about 20 kilometers wide and with the mass of a 1.5 suns that spin often very fast, up to like 700 more times per second. And in spinning, they illuminate the sky with their beams, some sort of lighthouse. So what we see actually is a pulsed signal. These super dense stars with beams that illuminate the sky like a lighthouse. And this is a merger of research on pulsars and on so-called GWAPs, games with a purpose. So these are games designed to let the citizens do science in a different way than citizen science and citizen computing, where you involve people directly, for example, in the beautiful classification work that Galaxy Zoo was doing, or just use their resources like Boeing. A GWAP, a game with a purpose, transforms the physical objects or the chemical interactions into game objects that people interact with, sometimes even not knowing that they're interacting with molecules or proteins, like in the case of Folded. Let me give you an example of what are the difficulties in pulsar searches usually. First of all, the radio signal travels through the interstellar medium and it arrives at different times at different frequencies. So if you don't correct for this, you will not see most pulsars because their signal will be washed out. Also, pulsars are usually, the pulsars we find now are pretty weak compared to the background noise, background radio noise, both instrumental and celestial radio noise. So we need to find them by using Fourier analysis. It's the typical way to find periodicities. We do a power density spectrum, we find peaks, we sift through them, eliminating harmonics and broadband noise and all this kind of stuff. And we use an accelerated version of the Fourier analysis. So for frequencies that are changing over time, to find pulsars that are changing their frequencies, either because they're spinning up or because they are in an orbit. So the Doppler effect is changing their frequency. Once we find a promising candidate, we run an epoch folding, which is cutting the light curve. You see the light curve here cut in many pieces, right? And stacked and summed in phase. And if we get the right period, then the signal sums with signal linearly and the noise sums with noise. So we gain in signal to noise ratio. There is a way to make this process extremely fast and even use it in place of the Fourier transform, which is called fast folding algorithm. It's an old algorithm, like 1969, that basically combines the steps of the folding in pairs of sums, so that we can get many different foldings by shifting the second block we are summing by a certain amount. CICLOPS starts from here. So CICLOPS is a game that uses modern technologies. It's based on the real-time development platform Unity for the building of the game. Most of the libraries are written in C# because that's what Unity uses, and most of the demonstration libraries we built to develop the algorithms and the server are written in Python. Starting from the fast folding algorithm, we can notice a couple of things. The most important thing, I think, is that there are intermediate steps to the fast folding algorithm. And these intermediate steps contain some already aligned signal, okay? So we can use this method by, instead of running the whole fast folding algorithm together, we can stop at the intermediate steps and have similar objects coming out of it. Now, in the first case, a single burst, you can have a fast radio burst, other interesting objects, other interesting signals that are practically indistinguishable from single pulsars. A single burst will happen before combining anything. So you will just take this chunk of data and you will be able to measure a single burst. In the intermediate steps, you will notice that we can find transient pulsations. For example, pulsations that are only happening in the first half of the observation or in some part of the observation. And at the end, we'll be more sensitive instead to persistent pulsations, the ones that last for the whole observation. All of them will have the same approximate shape because many pulsars have these peaks. They can have a sinusoidal shape, they can have many different shapes, but for the sake of simplicity now, I will say that all of these will have more or less the same range of shapes, and they'll have the same effect of dispersion. So we can try to basically change the order of operations in a typical pulsar search. To correct for the dispersion, we would make the dispersion the first step. And then on all the dispersed time series at trial dispersion measures, we would run an accelerated search, which is the Fourier transform, and then find candidate and then sift and then do everything else. Here, we take the dispersed time series, so we don't apply the dispersion initially. We run the fast folding algorithm and we run the dispersion on each single block. It seems like a waste of resources, but this actually allows us to transform each of the fast folding algorithm steps into game objects that we transform into asteroids. So everything you see here is one of the blocks of the fast folding algorithm. Actually, all of them comes from no blocks of the fast folding algorithm, but from the initial time series, because in this case, we're finding fast radio bursts. And you'll notice that all these asteroids have different smoothness, different dimensions, different colors, and different glow color. All of these map to a different statistical indicator that we've computed in the computer of the gamer automatically. And you'll notice that here there are these two blocks that are a little different from the others. They're bigger, they have a specific glow color. These two, I'd say, are good candidates for a search. At this point, well, there's a whole story. Of course, it's an adventure. You are in a spaceship. You are inside an asteroid field, and you take the asteroids and you put them into some machine where you have instruments to interact with them. And you'll notice here that with your instruments, you are able to make some stripes appear here. And this is actually the signal of a fast radio burst that you're trying to uncover here. For now, we have only two instruments, but we'll have more. Of course, this is still in heavy development. The structure will be a central server or multiple central servers if we need that send a series of simulated and real data. The simulated data need to evaluate the player. So the players that will be more able to classify uncertain signals will be given harder tasks to complete, for example. So there will be a part of training and the part of classification. Moreover, the clients will calculate the statistics for us and will make the combinations of matrices that are needed for the fast folding algorithm for us. So in practice, we'll be doing a GWAP game with a purpose that does citizen science and citizen computing as well. So the computation will not be done completely by our central server or servers. Heavy development, and we're trying to get Horizon funding. We were very well evaluated, but still not much, no acceptance. The Python analysis software was released into a couple of different time series analysis packages and are open source. The C# part will be half covered by proprietary licenses because it's heavily based on commercial products. And there are a couple of papers in preparation, so stay tuned. I want to just leave you with the list of people that have worked to produce this work. Thank you very much.
Thank you, Matteo. And I play big applause for your presentation. And I see in the Q&A actually no question, but I would have actually one. You're representing a multidimensional data with an asteroid, right? And have you considered, would there any kind of other representation which might be more or less, suitable for the classification by humans?
Oh yeah, we've thought about many different objects and many different game situations. This was you need to consider many things. One is the affordance of game objects. So the way a game object suggests the way you use it. The other is finding game objects that allow you to change their shapes according to many different indicators. You can put as many indicators as you want. And also game objects that allow you to see a lot of them and point out the ones that are more interesting. So let's say that asteroids were an easy way to achieve this. Future developments might lead elsewhere. Now, this is in a demo shape, and of course, there might be changes in the future.
Okay, thank you very much.